Welcome back. So we are about to start Professor Joswig's third lecture. And so we are looking forward to tropical convexity today. So really looking forward to it. Yeah, over to you, Mikhail. Thank you so much.
Yes, thanks again for the introduction. And indeed, so the third topic will be about tropical convexity on consensus trees. So on Tuesday, we had a discussion about tropical linear programming. And so there you already saw tropical polyhedra. So these are tropically convex sets. And now we would like to study this in more detail from a combinatorial point of view. And there are many reasons to do that. And one of these reasons is recent joint work expressed in recent joint work with my PhD student, Andrei Komanec, where we discuss a specific problem arising in phylogenetics. Okay, so since I was switching back and forth between min and max conventions, actually for a good reason, I explained a little bit of this on Tuesday. So a role is the order relation. But there is also another aspect. So sometimes it's important to consider min and max together. And so we will see this today. And so here I already made a mistake because I wanted to define the symmetry with respect to max. So this is a typo. Right, so I was writing it here. So T is now the set R union minus infinity, and I take max as the addition like I did on Tuesday, and plus as the multiplication. So now I define what a tropical cone is. So a tropical cone is a set in R to the D, which is closed with respect to all tropical scalar linear combinations, with respect to all tropical linear combinations. And so this makes sense because the scalars are inherently non-negative. As we saw on Tuesday, every real number is strictly larger than minus infinity, which works as the zero. So, but because this looks like just an ordinary linear combination, so these tropical cones to some extent behave like linear spaces, and to some extent they behave like objects of convex geometry. And so this kind of twin behavior, this is owed to this observation. Now here's a key observation, which is very simple. If you have a tropical cone, then you can see that all scalar multiples of the all ones vector are contained in this set. So I should say a tropical cone is supposed to be non-empty by definition, and then it contains the all ones vector multiplied with any real number. So we can factor this out. And then here's the central definition due to Mike Devlin and Bernd Stolpfers from 2004. So where they say a set is tropically convex, subset of the tropical projective torus, if it arises as the image of a tropical cone under the canonical projection map. So the terminology back then, almost 20 years ago, was slightly different, but so this is now the established notation. And it's only a very mild modification of the original terms. So, and a tropical polytope is a finitely generated tropically convex set. It's easy to see that you can easily get a hull operator from this tropical convexity. So the tropical convex hull of any set inside the tropical projective torus is the smallest tropically convex set containing the given set. And then you can ask for finite generation, and then these are tropical polytopes by definition.
Mikhail, don't you need that lambda and mu to be in non-negative, in the non-negative reals, or in the definition of a tropic?
No, absolutely not. I want to have it exactly like this. And I said this so because in the tropical sense, all real numbers are non-negative. Right? So The zero element is minus infinity, and each real number is strictly larger than minus infinity.
Yes.
So, and if I take minus infinity as well, so then all elements of t are larger or equal to 0. So,
okay,
which is minus infinity here.
Yes. Okay. Okay. Thank you.
So this is, it's really what I mean here. All lambda and mu. All right.
Yes.
So, and so then this is the definitions. And one thing which is important, that there has been, or there still is, a subject called Max plus linear algebra, which was considered as a subfield of optimization, bordering functional analysis, because there's also a connection to operator theory. And so this predates tropical geometry for a long while. And so here I'm just writing down 2 references, which are monographs on this subject, which existed way before tropical geometry. So, and the purpose of this lecture today is to explain so what was added by Devlin and Sturmfels to this idea, and in my opinion, this fundamentally changed the subject, even if it was studied for decades before. So up to now, nothing happened yet, but we will see what is new in this definition in a second. But before we do that, so let's look at a few examples. So here I am looking at the plane. So the plane is now the tropical projective 2 torus. So R3, I have 3 homogeneous coordinates, and I mod out all multiples of the all ones vector. And now the pictures are obtained from turning the first of the 3 homogeneous coordinates to 0, and taking the second and the third coordinate as the x and y coordinates that you see in these pictures. So this is how these pictures will work. So you just, in the class x plus r times 1, you pick the representative, the unique representative with x1 equals 0. Okay, and then here are 6 examples, which are a little bit different, but also have some things in common. And on the lower left corner, so coined D, you see an example of a tropical half space like it occurred on Tuesday. More importantly, for the purpose of today, the top 3 examples are different from the bottom 3 ones, because the top 3 ones are finitely generated. In fact, all of them are triangles, so there are also more complicated tropical polytopes. But just to bring across that even just stupid triangles can attain very different shapes in the tropical world. So you see these 3 examples. And what is also important, that sometimes in this projection that you're seeing here, these tropically convex objects are also convex in the usual sense, and sometimes they are not. Right, and also, so example E is another triangle, but that triangle is not finitely generated as a tropical polytope. It's not a tropical polytope, and yes, so like this half space and this funny example to the lower right. So these are also not finitely generated. I should point out that there is also a version of tropical convexity in the compactification of the tropical projective torus. This would then be the tropical projective space that we also saw on Tuesday. And there, the compactification of the tropical half space would be a tropical polytope in that compactification. But that's nothing that I would like to discuss today. So for the purpose of today, everything just takes place in the tropical projective torus, and then the top 3 examples are finitely generated, and the bottom 3 ones are not. All right.
So picture E, why is it not? Can you explain a bit that if
yeah? So all the points on this diagonal are extremal in the sense. So for the generators of this guy, right? So if you take this point over here and this point over here, then the tropical line segment between these 2 points is this edge, right? But if you take any point on this diagonal here and any other point on this diagonal here, again, so the line segment just goes into the inside, and you never reach any of the other points. You need all the infinitely many points on that diagonal as generators. And so in this sense, it is no different than this example. So here the generators are this infinite set, so on this curved arc, plus this one point here.
So why can't we define convex sets as in the usual sense that given any 2 points, then there is a unique line, right? Tropical line passing through 2 points. So
exactly. So exactly.
So we can define the tropical convex sets as being closed with respect to taking line segments.
Yes, this is true. So this is equivalent to the definition that I gave, but then you still need all these points on this diagonal as generators. Because the line segment is a piece like this, right? So a line segment. So I mean, there are 3 ways how you can have generic line segments, but the thing is that the straight line, which looks like a straight line here between 2 points on this diagonal, is not a tropical line segment.
Yeah.
Right, because
exactly. Yeah.
the slope is wrong.
Right. Yeah.
Okay, so these are these examples, and now let's go back a little. Let's talk about tropical hyperplanes. So tropical hyperplanes are defined as the hypersurfaces corresponding to linear forms. So, and then here's just a tropical linear form, which is given by d real numbers for the coefficients, and then the tropical evaluation at a point x in this form is the evaluation of the tropical linear form A at x, just like a standard scalar product, but just tropically. Now, if you will now ask for the set of points set of points x where this expression attains its maximum at least twice, then for d equals 3, so again 3 homogeneous coordinates, then you get a planar picture. Then this picture looks like this. And so it's easy to see that because you always have this special point minus a. This point minus a obviously is contained in this tropical vanishing locus, because if I replace x by minus a, so then all the d terms evaluate to 0. That maximum is clearly attained more than once. So that's why the point minus a lies on the tropical hypersurface. And now, if we have 3 homogeneous coordinates, you can pick 3 coordinate directions where you leave 2 of the coordinates values at what you get from minus a, and then you increase the third one. And so you have 3 directions in which this line extends, and this is how this picture comes about. And so this is, just to remind you, so this is just the tropical setting for the max operation. And and the similar thing for the min operation looks like this. So it's a mirror image. So this is important. So because very soon I will now mix min and max. All right. So, okay. In general, it's a tropical hyperplane is a codimension 1 polyhedral complex, and so here just hyperplane in the plane is just a line. Okay. Here's now the key theorem, and as I said, so the key result is due to Develin-Sturmfels, and so they explain what tropical polytopes look like combinatorially. So there are various objects now, and I will explain them hopefully carefully enough. And these objects are all generated just from a matrix of real numbers. So I will try to keep the parameters the same throughout this talk. So this is a D by N matrix, and I would like to see this as a sequence of column vectors. So I have N column vectors in R to the D. Okay, but they are labeled. That's why I put them in a matrix. So now there's one way that I can do that. So I can take each one of these vectors, and I produce a hyperplane with respect to min, such that this this column vector becomes the apex, the special point that you saw before. So here in this picture, these points minus a, these are the apices, such that that column vector becomes the apex of a min-tropical hyperplane. So then I get one min-tropical hyperplane for each column of my matrix V. So I get a min-tropical hyperplane arrangement, and that hyperplane arrangement just chops up my tropical projective torus into polyhedral pieces. And that polyhedral decomposition that I get is called SV. You'll see several pictures later. So, but it's I have the matrix V. This gives me this hyperplane arrangement AV and a polyhedral decomposition of the projective torus. Now, there's a third object, and this is sigma V. And so the sigma V at first comes from a completely different world. So now I'm forgetting tropical geometry for a second. I'm thinking about classical polytopes. So now delta D minus 1 is the convex hull, usual ordinary convex hull of the D standard basis vectors in R to the D. So they lie in a hyperplane. And so therefore, so this is just a regular D minus 1 dimensional simplex with D vertices. And similarly, delta n minus 1 is a regular n minus 1 simplex. And now the polytope that I'm producing is a product. So it's a Cartesian product of two polytopes and so the dimensions add up and the number of vertices multiply. And that's just a standard polytope which occurs here. Now, what I do with this polytope and my matrix V. So if you do the count, then you see that the number of vertices of that ordinary polytope is exactly D times n. Exactly the number of coefficients in my matrix V. So now I take for each vertex of the ordinary polytope product of simplices, I pick the corresponding coefficient of my matrix V, and I consider this a height function. So I start out with a polytope in D minus 1 times, D minus 1 plus n minus 1 dimensions. I add one more dimension via this coordinate. Then I take the convex hull. I get a polytope, ordinary polytope, no tropical geometry. And then I'm just looking at all the faces which have downward pointing facet normal vectors, where downward refers to this additional dimension that I took for the height function. So then I project this down, and what I obtain is a subdivision, and this is a definition of a regular subdivision of this product of simplices. And so, now the statement says, so these three things are essentially contain the same information. So there is a duality going on. I don't want to make this precise for the moment. I will do this in pictures, and later I will be more precise. So the polyhedral decomposition of the space of the tropical projective torus that you get from the matrix, this is dual to this regular subdivision of this product of polytopes, despite the fact that these two things live in different dimensions. It's not a mistake. And then, so why is this related to tropical convexity? Well, you can find back the tropical polytope that I produce as the tropical convex hull of the columns. I can't find it back as a cell in this as a union of cells in this polyhedral decomposition SV. All right. And this is the structure theorem of tropical convexity, and this is the difference to Max plus linear algebra, because this is something that got unnoticed before, and this is the game changer in this for this kind of math. There's many more things to be said. Most importantly, it is important that here in the first statement, I'm talking about min tropical hyperplane arrangements, and in the second statement, I'm talking about max tropical polytopes. So this is the first comment. And then there are various generalizations into various directions by various people. All right. So let's look at an example. This is kind of the first non-trivial case. So here, what I'm writing down here works for d equals 2. So then I'm working in R2 mod R1. So this is a line. So I'm just working on a line. I'm considering n points, n is arbitrary on a line. And so the picture refers to n equals 3. So what is the ordinary polytope? So the ordinary polytope, which is a product of simplices, is just a prism over an n-1 dimensional simplex. So what are ways to triangulate that guy without, or so with respect to, without new vertices? Well, so they correspond to the n factorial labelings of the n vertices of an n-1 simplex. Let me sketch that for you. So for this, I'm using this picture. So if I want to triangulate this prism, so I start here with a front triangle. So the front triangle is a boundary triangle. If I don't have additional vertices other than the 6 vertices of this prism, then you need to ignore this red triangle for a short moment. So then I just look at the front triangle. So then there's a unique tetrahedron in the triangulation which contains the front triangle. Necessarily, it must contain one of the vertices of the other triangle in the back, right? And then there's exactly one facet of the tetrahedron that I have. So in this case, it is E1. There's exactly one facet of the tetrahedron which does not lie in the boundary. And so this is this facet, so E1, E3 dash, E2 dash. And again, there must be a unique vertex in the back triangle, E3, which forms a tetrahedron in the triangulation with this guy, and so on and so forth. And so this proves several things. So in particular, then the choice of the triangulations of the prism that you get in that form just depend on the order in which you pick the vertices on the back face. And so eventually you need to take them all. And so therefore the permutations of the vertices of the back face parameterize these triangulations. Also, what you can see is there's a linear group action on these triangulations, which comes from the symmetries of the prism. And then this is transitive on all these triangulations. And now if we pick one such triangulation and we form the dual graph, right? So this hints to the duality that I mentioned in the previous result. So I'm looking at the abstract graph for now, which takes the 3 tetrahedra in the triangulation of this prism. In general, these will be n. But so here are 3 triangles. And I form the abstract graph where these tetrahedra form the nodes. And if the tetrahedra share codimension 1 face, then I take an edge, and in this case, I get a path with 3 nodes, right? So this is the dual graph is a path with 3 nodes, and in general, path with n nodes. And this is exactly the combinatorics of a tropical line segment, and that is the max tropical polytope that was mentioned in the previous result. And so the structure theorem says this. Yes, this is kind of the first non-trivial example for this kind of thing, but it's not a coincidence. It generalizes to arbitrary number of points and arbitrary dimensions. We will see more examples later. Okay, but this is the first non-trivial example. And now for the red triangle. So if you want to keep track of what is going on in this triangulation, then this 3-dimensional picture is unnecessarily complicated. And so I can describe the combinatorics, meaning the number of cells and how they intersect, just by picking a hyperplane which is parallel to the front and back triangle, and intersect everything that I get, all the 3 tetrahedra, with this new triangle, which sits in the middle, the red triangle. And then you see that the lower triangle that you see here is an intersection of the first tetrahedron that I had with that plane, and then this parallelogram is an intersection of the second tetrahedron with that plane, and then the back triangle so the final tetrahedron intersected with that plane is exactly the top triangle that you see here. And so the three tetrahedra in the consecutive order are share codimension 1 faces, and the same holds true here, right? So you see, so you can really see the tropical line segment in the dual graph of the red subdivision of this triangle. So this is again not a coincidence for the experts. So this is an instance of the Cayley trick. So we have so these subdivisions of product of simplices are related to mixed subdivisions of dilated simplices. And I don't want to go into the details for too much, yet I will come back to this later again, and I will explain the same picture in a different way. All right, so this is the first example. Other questions?
Questions?
Okay, let me.
Yeah, good for now.
So is there a question?
Yeah. No, there doesn't seem to be a question.
Okay,
yeah,
so
maybe we can slowly.
Okay, so then let's do another example. So this is slightly more interesting. So now I cannot draw this this product of simplices anymore because this is too large. My parameters are d equals 3, n equals 6. So the dimension of the polytope would be 2 times 5 would be 10, right? So the corresponding picture corresponding to the prism would be 10-dimensional. That's too much. But I can still draw so what happens in the tropical projective two torus in the plane, right? So, and I picked a matrix to make my life easy. I picked already for my homogeneous coordinates, I picked them with an initial 0 such that I can relate the tropical homogeneous coordinates easily with the Euclidean coordinates that I see in my picture. Right. So for instance, and then so I have 6 points, and for instance, the first column is this point over here labeled 1. As you see, it has coordinates 2, 1, like here. And so the second point is labeled 2, and it has coordinates -1, 0. And so this is what you see here. And now. And similarly for all these 6 points. Now this structure theorem, so let's go back to the structure theorem. So it talks about this polyhedral decomposition and this min tropical hyperplane arrangement. So, okay. So now, so here you see how a min line looks like. So this shape, you need to look for these kinds of shapes now, right? And you see you have one such shape for each column of the matrix V, right? So for instance, this is the tropical line, which corresponds to this first thing here, and the apex sits directly at the column. And similarly, you get six of these. On purpose, I picked an example which is not in general position for the experts. Okay. So, so you get this hyperplane arrangement, and you see that you obtain a decomposition of the tropical projective two torus in terms of ordinary polyhedra, right? So these are ordinary convex polyhedra. Some of them are bounded and some of them are unbounded. So they form a polyhedral decomposition. This SV that you saw before. And now, so this SV is dual to this subdivision of the product of simplices, like you saw in the in the previous picture. But also the second statement of the structure theorem said, well, so this helps you to find the max tropical convex hull. And how do I do this? Well, I have all these cells. Some of them are bounded, some of them are unbounded, and I take all the bounded cells. This is what I get. So now this thing. So this is everything which is marked now, and this also includes this one-dimensional piece and this one-dimensional piece, everything. So the two-dimensional cells which are shaded plus these two one-dimensional pieces, they all together form the tropical convex hull of these 6 points in the plane. And you see a polyhedral subdivision that you see here, which is induced from this tropical hyperplane arrangements, and this comes from the generators. Also, it is important to notice here, so that for the tropical convex hull, the columns 2 and 6 are redundant. So you do not need them for the tropical convex hull, yet they are there, and so they contribute to the subdivision. So you could argue from a complexity point of view, these are unnecessary. They make the subdivision unnecessarily complicated. But for the statement of the structure theorem, this is what it is. I mean, so you really take the generators that you have, and then they contribute to the subdivision, even if you don't need them for the tropical convex hull. So this means, the 6 points, 2 of them are redundant for the tropical convex hull. So this is a max tropical quadrangle generated by 1, 3, 4, and 5. All right, so this is our second example. And now, so there are many things to be said about that. And so so in particular also, these products of simplices occur elsewhere in geometric combinatorics and with applications to algebraic geometry. And therefore, people have been studying them again much before tropical geometry. And so people have been writing pieces of software to deal with them and to enumerate them. And so here are the known counts of all triangulations or regular triangulations of products of simplices up to symmetry, right? So you have the product of symmetric groups of degree d and n respectively acting naturally on this product of simplices. And with respect to that group, you can look at orbits. And then the first example that we had, these were these prisms. So this corresponds to the first row of this diagram. And so there everything is boring because up to symmetry, there's only one triangulation. So this is why we have a 1 in the first row here. And then this table only gets interesting for those 3 and 4. And so the black numbers, so these are known for quite a while, and they actually already occur in the original paper of Devlin and Sturmfels. Some of them have been computed by Dan Sturmfels' former PhD student, Jesus de Loera, with a Maple program called Puntos. And there's an industrial strength solution known as TopCom due to Jörg Rambau. And that computed all the black numbers. And so like 4 years ago with Skip Jordan and Lars Kastner, we built a new version of an algorithm. It's a different algorithm than the one used by Topcom to enumerate these types of triangulations. Yet we do use some pieces of the beautiful open source software system Topcom. So therefore we called it MP Topcom, MP like multi-parallel. So there's a non-trivial parallelization aspect plus a few more things which went into this piece of software. And so with this, we computed these 2 blue numbers. And so this is everything what is known about them. So in particular for d equals 5, we do not have any of these numbers. And so this is also the reason for producing the first trivial row here, such that you can appreciate the tremendous growth in each column, right? So whatever should be expected for the next value 5, 5. So this is then the next term in a sequence which starts like 1 is the first entry, 530 is the next entry, and 7 million something is the third entry. And now you're free to guess what the fourth entry of the sequence should be. It will be huge. Okay, that's the only thing. I only have trivial bounds that I could tell you, and they are so stupid that I don't even share them. So we don't have a good guess of what the next number should be, and it's most likely that we won't ever get at them within our lifetime. All right. So this is, so if you want to study these combinatorial types, so this is interesting for a number of reasons, because this is related to other classification problems. But now let's see where this tropical convexity occurs in nature. Actually, one example you already saw on Tuesday. So it does play a role in tropical linear programming. So I hinted at the end of my lecture on Tuesday, I hinted to a connection between classical linear programming and tropical linear programming, and in particular non-trivial complexity questions. And in order to exploit, to really prove something non-trivial there, you need to rely on this combinatorial aspects of tropical convexity quite a lot. but the technical details are a little bit ramified, and that's why I'm talking about something else here. Okay, so I will now start over with something entirely different, right? And of course, I will come back to tropical convexity in a second. So here's a classical problem in mathematics that was studied for a long time. So Fermat worked on it apparently, and then Weber picked up the subject at the beginning of the 20th century. And this is a topic which can be studied in any metric space. So what is the problem? So you pick your favorite metric, and then you also pick a metric space, and you pick finitely many points, which you call sites. And then you want to find another point which minimizes the sum of the distances to the given sites. In general, that point is not unique. So this is a Fermat-Weber point. And so the set of all such points is a Fermat-Weber set. And this has been studied for a number of reasons for various metrics. And you can imagine there are numerous applications, right? So typical application is in point location or site planning, right? So imagine you have a town, and then the sites are just houses where people live, and you want to plan a new hospital, and then you want to minimize the distance that people need to travel in order to get to the hospital. And this is exactly a Fermat-Weber problem. And you can easily make up other examples. Now, we want to study this for a specific distance function, which occurs in tropical geometry. So this, for instance, this occurred in work of Omid Amini and Manjunath on relationship with Riemann-Roch type theorems in tropical geometry. And so this is an asymmetric distance function that is given like this. So initially you can define it for arbitrary points in R to the D, but very soon I will restrict them to make my life a little bit easier. So, and the key thing is that this distance function is not symmetric in X and Y. So if we come back to this hospital example, it is perfectly natural for these Fermat-Weber problems to consider non-symmetric distance functions, because it is a difference if everybody wants to go to the hospital or the hospital wants to come to you, right? So these are two different things. Also, on a standard grid of a street network. So then you have one-way streets. So these are typically two different distances, and sometimes one of them is more important than the other. Okay, so much for that. So the first simplification that we do is, so instead of considering arbitrary points in R to the D, we now take points in R to the D whose coordinates in the classical sense, ordinary sense, sum to 0. Okay, and so then again, it is easy to see that this is just another model for our tropical projective torus, meaning in each equivalence class RD mod R1, you find a unique representative with this condition. And so this is a little bit easier to work with. In particular, you see that then in this case, these sum terms in the beginning just vanish, and you are left with a more simple expression if you restrict your attention to this thing. And I can apply tropical convexity to this model of a tropical projective torus. So now I pick a finite subset, which is again called V. It's not a coincidence.
There is a question. Sorry.
Yes, please.
So in the last phase, there is the distance function defined. So how both are related, like here it is defined in H, and in the last phase that was summation of yi minus xi minus d of minus.
The question is, so in tropical. So what is the question? Is it referring to this slide, or is it
in the last slide? Yeah.
This.
Yeah. So there is the distance function, which is summation of yi minus xi minus d of minimum of yi minus xi. So from here, okay, it is defined in RD.
So this is just a definition. And now if I restrict to points which lie in H, so then, I mean, this sum is 0 and this sum is 0. And so is this the question?
Yes, yeah, thank you.
Okay, so I should also point out, so there's in tropical geometry, there's sometimes another distance function. And I will come back to that in a second. But let me first continue. So now we can pick an arbitrary finite point set lying in H. And then I can define this minimization problem that I mentioned. I take the distances from those points to X. So now I have two different Fermat-Weber problems because my distance function is not symmetric. So the first problem is where the sides are in the first argument, and the second one would be where the sides are in the second argument. And so these two choices, if you look at the formulae, so if you exchange X and Y, so then you see, in fact, there are two of these distance functions, one with respect to min and one with respect to max. So the one that I'm picking is the max version, and exchanging these the arguments here would refer to the min version actually. And then if you have the two things, then you can form the average of these two asymmetric distances, the max tropical distance and the min tropical distance. And this is the symmetric one, which has been studied by many other people before. So the other one, the symmetric choice, is more common than this one. But I would like to argue that this is, for some applications, the correct one. And the symmetric one is more unnecessarily complicated, and it has some undesirable features. So, but I should point out that this Fermat-Weber problem has been studied before by Lin and Yoshida for that other distance function. So there are results for that distance function which are different from ours. Okay. So now the key result, there's a whole sequence of results, but so let me just pick out one. So the key result says, well, these tropical Fermat-Weber sets with respect to this asymmetric distance function are tropical polytopes, max tropical polytopes. And so there's making use of the structure theorem of tropical convexity, I can say absolutely precisely what the Fermat-Weber set is, right? So we had this sigma v, which was the regular subdivision of the product of simplices. That is an ordinary polytope which has a vertex barycenter, right? You sum all the vertices that you have, the d times n many, and then you divide by their number. And then that point is 1 over d times the all ones vectors, comma 1 over n times the all ones vector. That's like the middle point. But also in this case, it's also the center of gravity in a measure theoretic sense of this polytope. And so we have this sigma v, which is a regular subdivision of this ordinary polytope, and it has cells of various dimensions. And then these cells are polytopes, and we can look at the relative interiors of these things. So the relative interiors are relatively open polytopes, finitely many, and the relatively interior polytopes, so they partition the entire product of simplices. So if I have a specific point, for instance, this vertex barycenter, then it is contained in a unique cell in its relative interior. And then, and that cell is the one that I want. And so the theorem says the Fermat-Weber set is exactly the dual to that cell. So you could call it, so it is like in the tropical convex hull, it is the thing which sits in the middle, where in the middle is defined via this vertex barycenter construction. And also it turns out that this is a bounded polytope. It's not a typo here, so it's a polytope which is at the same time tropically convex. So these are sometimes called polytrope. If they have integral vertices, these are sometimes called alcove polytopes in the literature. And but the Fermat-Weber set is such a polytrope, and it is contained in the max tropical convex hull. And again, we will see an example. There's many more things to be said. In particular, so there are two things which are important. We can say something about the dimension of the Fermat-Weber set. So because it is dual to a cell, so it has an honest dimension as a convex polytope. So the Fermat-Weber set is a convex polytope also. And it has an ordinary dimension, and that dimension is at most the GCD of D and N, the two parameters minus 1. And also that bound is tight. So this means for all D and N, there are point sets V such that the Fermat-Weber set attains that bound. This is,
yeah.
yes.
Sorry, there is a quick question.
Yeah.
Can you please define a polytope again?
Is a tropical polytope which is also convex in the ordinary sense, right? So like in this here in the beginning, so the hexagon in the top middle and the triangle in the top right, so these are tropical polytope which are also convex in the ordinary sense. So these two are polytopes, whereas this one is a tropical polytope which is not convex in the ordinary sense. That's why it's not a polytope.
Oh, okay. Thank you.
And the thing is, so here you see the bounded cells of this hyperplane arrangement are always from this of this form. So all of them are polytopes. So here you have 1, 2, 3, 4, 5, 6 polytopes that contribute to the tropical convex half. Okay, so this polytope. So once I know that it is such a cell, so then this polytope property follows from the structure theorem. All right, so we have the dimension bound, and so this is actually to prove the dimension bound and to prove that it is tight is harder than proving just the two statements which are here. So this is, I'm just giving you a simplified version of this theorem. And also there's another aspect, namely the Fermat-Weber set can be computed efficiently. And this is actually what makes it useful for applications. So this is, and I will say a word about the algorithm. I won't give the entire algorithm, but I will hint towards the algorithm a little bit later. First, I would like to do another example. So here's again a planar example, D equals 3 and N equals 5. So I have a matrix with 3 rows and 5 columns, and consider this as a sequence of 5 points in the plane. Previously, I picked representatives where I already had a 0 in the first row. Now I want to have representatives in this hyperplane H where all the coordinates sum to 0, and you can check that in each column the coefficients sum to 0. Right, so for instance, the first column, so 14 minus 7 is 0, and similarly for the other columns. Right, so there are now I have 5 points in H, so this leads to tropical polytope. This leads to a min-tropical hyperplane arrangement, and this leads to a regular subdivision of a 2 simplex times a 4 simplex, so an 8-dimensional polytope. So there's 2 things to be said now. First, what is the Fermat-Weber set? And in this case, it is just a unique point. And so, and this is not surprising that it is a unique point if you followed, so that because the dimension bound is given here, so the GCD of D and 5 is 1, and if I subtract 1, it's 0. So it's a 0-dimensional convex polytope. It must be a single point. So it already follows from the parameter that the Fermat-Weber problem does have a unique solution, which is not always the case, but in this case it does. Now, what's the relation to this tropical convexity? Again, I take these, I can take this matrix as a height function on this product of simplices. Then I have this 8-dimensional product of simplices. And then I can do the same hyperplane trick that I showed you before. Now it's a lower dimensional subspace that I need to intersect with, where I can see the beauty of this high dimensional subdivision in a planar picture. And that is the picture that you see on the right-hand side. So this is, again, the mixed subdivision picture for the experts for just a triangle scaled by 5. And so the subdivision that you see is a subdivision into these small pieces. So some are triangles, some are parallelograms, and some of them are trapezoids, which are not parallelograms. And so these are the various cells. And so their intersection pattern is exactly the same as the intersection pattern in the regular subdivision of the product of simplices. So as I said, so this is a mixed subdivision picture. And here's another way of seeing this, right? So the hyperplane arrangement comes from taking 5 tropical linear forms with respect to min, right? And then you take these 5 linear forms, you can multiply them tropically, so then you get a tropical polynomial of degree 5. Since and then the support of this tropical polynomial of degree 5 are all the lattice points in the standard triangle scaled by a factor of 5. So these are exactly these coordinates that are marked here. So that's the support of this degree 5 tropical polynomial. And then I can look at the tropical hypersurface, which belongs to this tropical polynomial, and this is exactly this union of these hyperplanes. In this case, union of these lines, and this is exactly the union of these lines up to piecewise linear deformation that you see here. And here again, you see this duality, right? So then, for instance, this guy, the orange guy over here, so this corresponds to the first column. And so this is a slightly degenerate tropical line that you see here. Here's another tropical line, and here's another tropical line. And here you see the duality at work with the help of the mixed subdivision. And now the Fermat-Weber cell is dual to the central thing that you see over here. So that's why this intersection point of the green line and the orange line. So this is exactly the unique tropical Fermat-Weber point. Okay, so this is how it works and how the connection to the structure theorem works. Now, for the remaining few minutes, let me do 2 more things. So first of all, I would like to say something about this algorithm. In order to get at a good algorithm for computing these Fermat-Weber sets, this is not the entire truth, but that's the key step. The Fermat-Weber problem can be phrased as a linear program. So that's what I'm doing here. So here, just so I'm transposing my matrix. So now the sites are in the transposed matrix. So Vij. So this is the jth coordinate of the ith point. And then I can phrase the Fermat-Weber problem as a linear program where the x variables, so it's a linear program in n plus d variables. So I have d variables for the point that I'm looking for. So the optimal solution is a Fermat-Weber point, that's the claim. And then the t's are the distances of that point to the given site, right? So ti is the distance of for the optimal x, ti is the distance of that point x to the point bi, and this is exactly the distance function. So the sum of the distances that you see here. And so I still have this constant. I kept this constant here. It is obviously not necessary for this optimization problem, but this is exactly how this comes about from the simplification of the distance function that I showed you. So there was this term d there, and I would like to keep it because in order to understand the linear program, I want to dualize. It's standard trick in linear optimization, and there you see that keeping the d is actually naturally. So this is a mechanical process which takes a linear minimization problem, turns it into a maximization problem. And so the n times d plus 1 constraints so become n times d y coordinates plus 1 lambda variables become the number of variables, and the number of variables become the number of constraints. So we have n plus d constraints, and then this is the function that we need to maximize. And now if you stare at it for a while, so then you have we are looking at a matrix with y coordinates, right? So yij, so these are the dual variables in addition to the lambda. And then so I'm looking for a matrix of y's with a property that each row sums to d. And then if I bring the lambda to the other side, I'm looking for a matrix of y's where each column sums to minus lambda. So, and this is the y's are non-negative, and so this dual linear program is a version of a linear program which occurs very frequently in the optimization literature. It's a so-called transportation problem. And so the good thing about transportation problems is there are many good algorithms known to solve these things efficiently in polynomial time in the parameters with low degree polynomials for the complexity. I don't want to give more details because there are several algorithms. Some of them perform better on this kind of input. There's, again, if you want to look up the details, again, the book by Schreiber is a good first approximation. But even after Schreiber, which is from 2003, there are many more results on transportation, and all of them apply here. Okay, and so these pair of linear programs is the reason that we have fast algorithms to solve this particular Fermat-Weber problem. So this is what makes this, and this something like this does not exist for the symmetric Fermat-Weber problem in the tropical Fermat-Weber problem. Okay, but I still have 2 or 3 more minutes, and now I would like to explain you why this is good news, this complexity result, because we actually want to compute Fermat-Weber sets. The context is biology, where we are interested in finding phylogenetic trees, and what you see on the left-hand side is a page of a notebook of Darwin, which is supposed to be the first visual of a phylogenetic tree. And so the more recent source is the standard textbook by Sample and Steele. Phylogenetic trees have been studied since Darwin and have been created by a number of techniques. And so in the age of phylogenomics, this is typically based on DNA data. And so what is known about the state of the art is collected in a very beautiful open source data project called Tree of Life. I'm giving the URL on the lower left corner. Check out the details. It's a lot of fun. And it contains a wealth of information about what is known about all the species and their ancestral relations. All right, now back to math. So there's a history of at least 30, probably 40 or more years of mathematics applied to phylogenetic questions. And one way to think about them, phylogenetic problems, is in terms of dissimilarity maps. So these are just symmetric matrices with L rows and L columns, and such that they have a 0 on the diagonal. Typically, we assume that these entries are non-negative, and then I can read them as kind of distances. In particular, if I ask for a strengthened form of the triangle inequality, namely the ultrametric inequality, which is so coefficient delta ik is at most the maximum of delta ij and delta jk for all choices of ij and k. So this is so then there are general dissimilarity maps, and some of them are ultrametrics, and these are the ones that I'm interested in, because these they correspond to equidistant trees. So this is known long before Bilera, Holmes, and Folkman, who looked at the entire space of these equidistant trees. So equidistant means, so if you we are talking about rooted trees, and then the distance, we can look at the distance. So we have weights on the edges. And then if the weight of a path is just the sum of the weights on the edges of a path, and the tree is equidistant if the sum of the weights from the root to each leaf is the same. So this is this equidistance property. And it is known that ultrametrics define equidistant trees in a unique way, and conversely, each equidistant tree gives rise to an ultrametric by measuring the distances among the leaves. So L is the number of leaves of such a tree in this thing. And Bilera, Holmes, and Folkman showed that this space has a natural topology, and it is non-positively curved with respect and a natural metric, and is not positively curved. There have been numerous attempts to relate this to tropical geometry, and a more recent one is due to Lin, Schlomfels, Tang, and Yoshida. Let me not go into the details. More important for our purposes is a result by Federico Ardila and Carly Clivens from 2006. And they gave a matroid-theoretic tropical geometry interpretation of ultrametrics. So namely, they said that so an ultrametric is exactly a point in the Bergman plan of the complete graph. And so the good thing about these things, so these are particular examples of tropical linear spaces, which are known to be tropically convex. This is the key thing. So the space of ultrametrics is tropically convex in a natural way. So this is an old observation, and this is why people in tropical geometry started to look at these phylogenetic things. And just to the comparison with the parameters as before, D previously was my dimension, and so I keep it like this, and the dimension is here now L choose 2, so the number of non-trivial entries of my ultrametric, right? So because it's supposed to be symmetric, I only need half of the off-diagonal entries, and this is L choose 2 many. Now, here's a theorem, again, from this paper with Andre. So if we take finitely many of such trees, right, so then we can look at the tropical Fermat-Weber problem on that tree space. It makes sense because it is a tropically convex subset of some tropical projective torus. And then this, as we saw from the previous results, so the Fermat-Weber set is a tropical polytope, and now it's a tropical polytope which is contained in that tree space. And also, so from tropical convexity, the structure theorem, we have the cell decomposition, and we know that this Fermat-Weber set is a cell in that natural cell decomposition, and therefore it's a consequence that any two trees actually share the same tree topology. And so this is what we proved. And let me do one example, and then I'll end. So here are three equidistant trees. So the three black trees, A, B, and C. And so you see the root at the top, and then the axis on the left, so measuring distance. And you see the distance from the root to each node is exactly 8. And you have altogether 9 leaves. So these could be 9 species, and they occur in different orders. So we have 3 different trees, which can come from various ways to construct trees for given data. So there's, even if you look at the same set of DNA data, there are many, many algorithms to produce trees. And there's a need to kind of decide where these trees agree. This is the consensus tree problem. And we are providing a new method to produce these consensus trees. And this is the red tree on the lower right is the tree that you get. The moral of the story is, well, so the tropical polytopes give you this natural cell decomposition, and applied to this consensus tree problem is good because it gives you a fast algorithm via transportation, and the resulting trees have a number of nice properties. And this is what sets this method apart from other methods. So other methods are either difficult to compute, or they have some undesirable properties, and I claim that this new method is superior. All right, this is what I wanted to share, and here are the references. So the first one is something that I didn't talk about. So we were talking about tropical polyhedra defined in terms of tropical inequalities on Tuesday. And today I was talking about tropical polytopes in terms of tropical convex hulls. So this is exterior and interior description of convex sets. And there's an algorithm to convert one into the other. And this is due to Xavier, Stefan, and Eric. So this is this thing. It's a tropical analog of a known method for convex hull computation. But this requires to work in the compactification that I mentioned. And then there's the second paper is the one by Bilera, Holmes, and Folkman. The final one is this, what started this entire field of tropical convexity. And then the second but last one is our most recent preprint on that subject that I just explained. Thank you for your attention.
Thank you. Thank you so much, Mikhail, for the very interesting talk. Questions from the audience?
Yeah, so you mentioned about the unique cell for the Fermat-Weber set in the subdivision. So
Yes.
could you comment on, like, there's this types associated to the cells by
Yes.
the work of Ayyer. So is there anything that you can comment on the type associated to that unique cell?
Yes. So this is related to, so this thing here, so this can be directly translated into type information or co-vector vector information, since we do not know exactly where this point resides. So it is easy to compute the type of that point, and so I wouldn't know it from the top of my head, but it's you can do this immediately. This is it's kind of equivalent to there's an equivalent formulation of this description in terms of these types.
So could you comment? Can you hear me?
Yes, I can hear you.
Could you comment on the types of results in biology, in evolutionary biology, one might hope to address using these methods?
We are currently talking to several groups of biologists who really are wet lab biologists who have actual data of their own, and we started to talk to them and want to process their data via our methods. So this is, I'm really heading toward actual applications to real world phylogenetic trees. That's what was on our mind.
I see, but what kind of statements or questions does one hope to address?
So biological questions. So people are studying these. For instance, I mean, there's a whole industry of people who are just studying phylogenetic trees for viruses for obvious reasons, including SARS-CoV-2 and friends, and typically they're trying to find trees on rather many taxa. So because there are so many strands of virus RNA in that case flying around, and just to keep track of it, you need to have methods which are efficient. And some of the methods which exist and are used in practice don't scale very well. And so one contribution that we have is our method scales, just because of the LP duality that I showed.
I see. I have another question. So you had this slide about ultimate trees.
Yes.
Could you?
This one.
Yeah. So if I, replace trees with buildings.
Ah, very good.
Some, yeah. Yeah, go ahead.
Ah, okay. So I mean, you probably talk about affine buildings of type A and tilde.
Yeah.
Okay, so there's no connection to tropical convexity. The question is, so that would be a universe, a tropically convex universe in which you could work. So, and what kind of objects would you like to study there? Just points, finitely many points, and then computing Fermat-Weber sets, or what would you like to do in the building?
I'm not sure I had something very specific in mind. There's some projects where we had to work with buildings.
Yes.
Myself, I'm not an expert on affine buildings, but we, convex sets of various types played a very important role. And I was wondering if, addressing that more systematically using the tropical convexity, is that something that people have looked at?
Yeah, that is indeed something that people have looked at, and so there's a notion of a membrane, which goes back to work of Hecking, Kiel, and Teveliev. And so this notion can be traced back to work of Faltings on arithmetic groups and factorizations and things like that. And and then there's a result obtained with Josephine Yu and Bernd Sturmfeld and myself many years ago, where we showed that computing these membranes is the same as a tropical convex hull operation. Interestingly, also in that context, it is natural to compute both min and max tropical convex hulls. So there is a known connection, but so this new result, so with this Fermat-Weber problem, that could be analyzed in that context, and that would give you a certain cell in this tropical polytope. And this is kind of distinguished, but what it should mean, if something in the buildings world, that I don't know. So, but it could be worth to explore. I don't know.
Thank you.
So the topology of these tropically convex sets, they're just simply connected, right?
Yes. Yes.
And what about faces and studying them in terms of, I mean, we can define faces of these, can we, or there is an issue?
The thing is, several people suggested various concepts of faces, including me. And so various people came up with various ideas, and they don't quite agree. And it's not as easy. Let me, so one result that you can prove, so I mentioned this on Tuesday, is you can see every tropical polyhedral and every tropical polytope as a projection of an ordinary polytope over Puiseux series with respect to the tropicalization map. And so you can try to inherit a phase structure from an ordinary polytope, but this is made difficult because the fiber of the tropicalization map is complicated, very, very big. So you have very many different combinatorial types upstairs, which tropicalize to the same polytope, tropical polytope. This makes it difficult. But I mean, there are some, it is not totally hopeless. And this is exactly what we exploited for this these complexity results in linear programming. If you restrict your attention to general position and you are just content with vertices and edges, so only the graph structure, then you can do it. And that is, but I don't know about higher dimensional phases, so it's not so clear. It's a little bit tricky. I mean, you could fake something probably by just defining something in brute force, like I did 20 years ago. But if this is really convincing, that's another story.
Okay. So all these questions that are about phase numbers in usual polytope theory and so on haven't yet been explored because of this, because there hasn't been.
That is true. But there's another, I mean, so there's a natural phase number here, which comes from this decomposition into these cells, right? So tropical polytopes are special examples of tropical linear spaces, you could argue. And so they have a decomposition into ordinary polytopal cells. So they have an F vector. And there's an important open conjecture due to David Speyer, known as Speyer's F vector conjecture. So, and this has been proved in special cases. So, but there's an upper bound problem to be solved. And that's very hard. But this leads you to matroid theory combined with, let's say, advanced techniques from algebraic geometry, including K theory and other things.
So what is this called again? Speyer's? What is the
Speyer,
name?
It's David Speyer. So it's this Speyer here. So it's David Speyer is a previous PhD student of Bernd Sturmfeld again at the same time as Right. So here's a wonderful paper. So from 2005, it's in Science Journal Discrete Math on tropical linear spaces, and there you will find his conjecture.
What is the name of the conjecture? You said something.
Speyer's F-vector conjecture.
F-vector. Oh yeah, F-vector. Right. Okay. Yeah. Yeah.
So I have a small small paragraph about this also in my book, in my tropical.
Okay.
So there you'll find the references.
Okay. Thank you so much. Yes. Questions from the online audience? AV team, can you please unmute them? Oh, okay. Oh, it looks like they were so many were around. Maybe some of them just left right now. Okay. It looks like there is nobody. All right. So thank you so much again, Mikhail. Any final questions? Okay. Thank you very much again for this very intriguing lecture. So yeah, thank you.